fun?
Yeah.
It's kind of scary, yeah, I know. Okay, I'd like to talk about for 7 minutes, and Alan's timing me, is what do drawing numbers mean? A drawing number, a big word for that is dimensions. That's what engineers like to call them. But you see frequently a part, and a drawing is a piece of paper that shows a picture of the part from multiple angles. This is all pretty simple stuff if you've already had this. So if you see 3 views on a part, it's not 3 parts, it's just one part, but you're looking at the part from different directions. So these are called orthographic views. You don't have to know that. Just as you see views that line up like this on a drawing, that's what it is. Because I've answered that question from a few students. But there's always a bunch of numbers on there. There'll be like, how big around do we want the holes? How far apart are the holes? Where are the bends? And it's easy to see what those features are, but it's hard to know how good to make them. Because in some cases, you don't care if it's off by a couple millimeters even. In other cases, you care a lot because stuff won't go together, such as you're building a gearbox. And the gear center lines are very sensitive about how far apart. So how do we talk about those things? It's really, we're talking about precision. Okay, I think of all machines as having 3 types of fit. And how you determine the precision is by how it interacts with other parts in an assembly. Like if you imagine you're bolting a wheel to a car hub drum, it's important that those 5 bolts line up with the holes in the wheel or it's not going on. So it's pretty simple stuff. But the key is I split them into 3 categories. One is a surface of the part or a feature of the part that does not interface with anything else. It's just in space. Like if I had 2 plates like this and I was going to bolt them together, I wouldn't care very much where the edge was. So I call those features clearance features, after my uncle Clarence, who owned an electric company in Flint, but I digress. The clearance, that means it doesn't touch anything when you put it together with the other parts in the assembly. The second type is called a fit, but there's no movement, fit parts or adjoining parts. What that is like a wheel on a drum. The 2 move together. There's no relative motion between the wheel and the hole, but they gotta fit. They gotta fit together. So usually fit involves hole patterns on parts. And there's 2 ways that we deal with that I'll cover in a little bit. The third type of surface is a lot harder to do, more difficult meaning, and it's a wearing surface. This is like a bearing surface where the ball and the ball bearing is rubbing on the track. That surface usually has features of surface finish. It kind of looks like a square root symbol in the dimension, which you'll probably get to later if you take design classes. But what that is that has surface finish requirements. Many people working on car engines don't understand this. They say, does my engine need rebuilt? And what they'll do is they'll measure the diameter of a piston. Well, it's not just the diameter, because if the piston surface or the main bearing surface is not properly prepared, that engine is going to have a very short life and it's going to really hammer you in the wallet in just a little bit of time. So for surface control or for wearing features, we tend not to make many of those unless they are slow speed, unless they are slow speed at the Technokats. The wearing surface is like a bearing that we would buy from a master car. Or a motor would have a wearing surface between the shaft and the bearing on it. And that's a part of the purchase assembly, so that those surfaces are designed to provide a long life with each other. So, but let's go back to fit, because clearance is pretty obvious. Nothing touches it, you're off a little bit, you don't care. But let's talk more about fit. Usually fit involves having hole patterns that adjoin each other, or you have a pin that goes through a hole or something like that. There's 2 ways to achieve a fit. Let's say you had 2 plates like this, or there's several ways. 2 plates like this, and you want them to bolt them together. Maybe there's a hole here. Imagine that this is a plate for a gearbox, where this is a gear bearing mount, this is gear bearing mount, and then these are the holes in the corner for the standoff bolts. Our tough boxes are made like this. Well, one way to make sure that that fit works good is by forming a stack. If you have 5 plates to make, you take 5 blanks or 5 just rectangles, you stack them up, clamp them together, and then you machine them all at once, going through all 5 at once on the mill. That gives you wonderful fit between the plates. That's probably the best way. The second way to provide a good fit is only put the holes in one of the plates. And then when you want to mount it to the other plate or bar or rod or whatever it is, you C-clamp it on there and then use a hand drill to drill the holes in the other ones. So even if these are off a little bit, it still goes together. So sometimes if you are working in my CAD models to generate drawings, because that's what we talked about last week, was that I want students to do that. 6 minutes, one more, I can do this. Is if you see something that goes together but there's only holes in one piece, what I am talking about is don't put holes in the other piece until you're done with this one. Then this piece can be made in something like a drill press. If you see something where all the holes line up like a gearbox, then fit is very important, and that should be done in a mill. But it's important, even though the mill 0, 0 is off the corner, for example, this edge is still not important. The main thing that is important is the relative location of the holes with respect to each other. If one of the plates is off just a little bit like that, if the holes line up, when you go to put it together, it'll still work and the bearings will not bind. So what this means is you think about these when you're deciding what to do. If you're cutting something with a clearance fit, there's no need to tie up a mill because they're in short supply, particularly if we get tailor people in here and other people working. So just go ahead and cut that with a bandsaw. Be tidy, but do that with something that's quick and easy. If you have fit, think about what parts of it fit. So here, like with these plates, you might blank them out with a shear till they're about the right size, clamp them together, and then these hole patterns that you want to be just right, you put those in the mill where you can very precisely control the head position. So you will hear me say things like clearance, fit, and wearing. And when you apply dimensions to a drawing, think about the way a mill works. Its dimensions, how you would set it up, and try to make it to where the student that's making the part doesn't have to do a bunch of math, to where it actually is, numbers are applied to the part in the same manner that that student would apply the machine tools to the part to make it. So it's really not hard when you stop and think about it. What's the right tool for this job? Should I use a mill, or can I use just a bandsaw because the mills are busy? You think about these 3 things. What are we trying to accomplish? And then you can easily decide what's important. It's really not hard. Okay? Is that pretty cool? People kind of understand that? It's good?